Yeah, okay. So today I'll talk about random polytopes and random partitions. Okay. So first of all, do we all know what a polytope is? Anybody? Do I need to explain what it is, or do you have an idea what a polytope might be? Just feel free to just unmute and just say it. What's a
Could you
polytope?
explain it? What is a polytope?
Yeah, what's a polytope? So a polytope is a well, it's a higher dimension version of a polygon. Okay, so a polytope is a convex hull of finitely many points. Okay, so you throw down a bunch of points in, say, RD, right? And then you take the convex hull, so that is like you take a cling wrap, right? And you sort of wrap it around your set of points. So you're gonna get like, like to sort of a thing that sticks out, in certain corners. It's very angular, right? And that thing is a polytope. Okay. So all right. So how do we construct a random? How do we construct a random polytope? Any ideas? Given the definition I just gave. If a polytope is just a convex hull of a set of points, how do I construct a random polytope?
Can you just choose random points?
Yeah, let's just choose random points. So let's think for now, let's think about polygons. Okay, so we all know what a polygon is. It's just a polytope in the plane. So if I want to get a random polygon, I can just throw down 100 random points in the square, and I take the convex hull, and now I end up with a polygon here that has 9 vertices, right? So take a cling wrap around this, and any point in the interior will not be a vertex, right? So technically you could have deleted that point and you still have the same polygon, right? But anything that sort of in this that supports your cling wrap is going to stick out, and that's called a vertex. Okay. So in this example here, I threw down 100 points. I get like 9 vertices. Okay. And you can do simulations like this. You take 1,000 points uniformly at random, and you take a polygon. How many vertices do you get in general, right? So that's the kind of question that people care about. So what can you ask a random polytope? You can say for a fixed n, let's say 100 or 1,000, or maybe even 4, right? I want to know what's the distribution of the number of vertices of the random polytope, random polygon, and what's the how big of an area of the, let's say, of the square does it cut out, right? What's the remaining area? Uh, uh, yeah. And there are many other questions. So this number of vertex is what we would call a counting question. This remaining area is questions about volume. So you want to think about vertices as like a 0-dimensional volume, right? So volume comes in different dimensions, and you can think of the 0-dimension volume as just counting number of vertices. The next dimension up is counting the perimeter, and then the next one is doing surface area, and then so on and so forth, all the way up until like the d-dimensional volume, which is the actual volume of your polytope. Okay, so these are the kind of questions that people, mathematicians, are interested in. So yeah, so let me just formalize the setup. I have endpoints. I sample them independently, uniformly at random from a square. And I want to ask questions about, then I get a polygon, and I want to ask questions about vertices and areas and whatnot. So all of this falls under the area of stochastic geometry. So geometry is study of geometric objects. Stochastic geometry is the study of random geometric objects, like random polytopes. You can so what exactly do we ask about those? Well, we want to study functionals, which are basically just think about them as like volumes, vertices, perimeter, surface area of a random polytope. So this has a lot of applications. I won't be talking about those applications. I'll just talk about the math part. So we're particularly interested in the case when n is, if you have an answer for finite n, then definitely you can have an answer for what happens to n goes to infinity. Sometimes the law of large number kicks in, our central limit theorem kicks in, and you don't have a good answer for finite n. Answer for any fixed n is complicated, but the answer for big N is really easy. So people really care about the asymptotic regime. Okay, so let me talk specific about this problem, right? Of throwing down n points in the square uniformly at random, and ask for the number of vertices. Okay, just the number of vertices. So that's a random variable, and I want to know what's the expected number of number of vertices. So this problem dates back to 1865. So here's a picture of Sylvester. It was known for the case n equals 4. It was known as the Sylvester's 4-point problem. Okay, so his question was slightly different. Well, it's almost the same as what I just said, except he threw points down in a circle. So Sylvester asked, if I have a circle, say radius 1, threw down 4 random points. Well, there's only, and take the convex hull. So there's only 2 options, right? Either I get a quadrilateral, like this picture here, or I get a triangle. Right? There's no, technically you can get all your 4 points lie in a line, and when you take a convex hull, then you get a line, right? The polytope is just a line with 2 vertices, but that case happened with probability 0, right? Because I'm choosing my points independently, uniformly at random from the circle. Technically, you could also get the case where all 4 points lie on the same point, and then the polytope just have 1 vertex, but also that's a degenerate case, cannot happen, right? With probability 1. So with probability 1, you're either in this regime or you're in this regime. So your expected number of vertices is somewhere between 3 and 4, right? And Sylvester asked, what's the exact number, right? Was pretty hard, very hard of problem of the time, and therefore it got a name. And that was kind of about the first problem in stochastic geometry as an area. So in answering this question, there was a lot of development in stochastic geometry. Anybody know what this is? This fish-looking thing? Any guess? Like, why is it here? Like, maybe Sylvester likes to eat fish, or There's a hint on what this is, right? You should read. Can you read like this? Around the fish, there's a circle with some words. Are there any words that you guys recognize?
The only thing I can think of is Nokia, like the phones.
Nokia, like the phones, exactly. It is Nokia, the phone. So Nokia, the company, which give us the phone right now. It's is it Finnish or Swedish? I can't remember. I'm sorry, but it was founded in 1865, I believe. So and it initially had something to do with fish. They were not dealing with phone at that time. I think they had something to do with like fish. So you can fact check me, but I'm pretty sure this was the company logo of 1865. Yeah, that's nice logo. Took, I don't know. This must be hand drawn, right? It's pretty hard. Okay, so fast forward 1865. We're now in 1963. So the field has moved on from Sylvester. Like for the 4-point thing, it's a certain integral. You can figure it out. Fine. Now what happened when n is not 4, right? But n is arbitrary. Let's say n is large, right? So there's no hope of like doing this integral calculation for large n. And so it wasn't until 1963 that there was like a satisfactory answer for the expected value of the number of vertices you can have by throwing down n points uniformly at random on a square and take the convex hull, right? What's the, you would get a v gone, and what is the expected value of v? The expected value of v turns out to be 2/3 times r times log n, right? So r, I believe, is the number of sides of the bounding box. So the bounding box in this case, when the bounding box is a square, then r is 4, right? So it will be 2/3 times 4 times log n. If you're throwing points not in a square but in like a hexagon instead, then you expect actually to have more vertices, right? If r will be 6 and so on, right? So it's very interesting that like the shape of the bounding box really matter. It's sort of kind of, well, it's not intuitive that should be true, right? It's not obvious at all, right? If I had a square and now I cut off like a tiny bit of the corner and now I'm going to get like an octagon, it's not obvious that suddenly the expected number of vertices I want to see is much larger, but it is, right? It's also, if you then believe that, you're like, then it's even more surprising that expected number of vertices only depends on the external shape by its number of edges, right? And not what the actual shape is. So you take like a very, very skinny rectangle versus like a square, then you're expected to find the same number of vertices from your random polygon, even though like the actual underlying shape makes the underlying area makes it very different, right? If you throw down points in a square, you expect like, you know, a roundish, you know, like a nice looking polygon like this. If you had like a square that's super skinny, then you expect like a very skinny polygon inside the red one. But the expected number of vertices turns out to be the same. So that sounds cool. So this is Ren Yi. He was a famous, I believe, Hungarian who works in, well, he's a famous probabilist. He did a lot of work in sort of a lot of work in order statistics. So worried about distribution of, let's quantize and maximize. Very, very classical. Yeah. This is 1963. This is, you know, this has nothing to do with Nokia, but it's I think it's a picture of computers at the time. So it's kind of amazing that, you know, well, it's like a computer would take up like a whole warehouse basically. So and that was when, you know, mathematically we're up to this level. So then we're up to 1988. Once you know the expectation, then probabilists would ask for the variance, right? And then they would get more ambitious and they get for the distribution. So this was, you know, completely resolved by this gentleman here, Professor Grunboom. He's a Dutch man, and his paper was, you know, published in, you know, like the best journal in probability. It's called Theorems. I think maybe the journal was Annals of Probability. I can't remember, but it's very good journal. The actual paper is called Limit Theorems for Convex Hull. It's very long, so I want to tell you it's 41 pages, right? 41 pages of mathematics in the 80s. It's pretty hard. It's pretty hard. The mathematics in the top journal by a top mathematician is pretty difficult. And I want to tell you that I will prove his result in this talk, okay, or at least give you a decent, you know, it's a decent idea of how the proof goes, right? So that, I mean, that goes to show that we're now have much better technology than just like a few decades ago, where we can now solve much harder problems or revisit, in this case, revisit old problem with new technology is going to give you much better proof. So what he found is that the variance is this thing. The expectation is 2/3, okay, times r times log n. The variance is 10/27 times r times log n. Okay, and you get a central limit theorem, right? So if you have done, anybody here has done like undergraduate probability? Yes, Lisa said yes, right? So maybe a few of you have done it. So central limit theorem said, you know, sum of IID, like sum of the number of hits in a, you know, sequence of independent coin toss, right? Toss coin, and do n tosses, count the number of hits, right? Then that thing, number of hits, minus the expectation divided by square root of the variance of that random variable, that converges in distribution to a normal. So this is, I mean, this is known as, for example, like the bell curve in social science, right? I mean, this is certain, the normal distribution has a certain bell curve. You might have learned about this back in like AP statistics or something. So it's not just sums of IIDs, it's other kind of, you know, random variable sequences of random variables can also have a central limit theorem. So this one in particular does, right? So you have Vn minus this expectation divided by square root of its variance, that convergent distribution to a normal. Okay, so this thing is a computer. Yeah, it's probably an Apple in 88. Yeah, so okay. All right, so that's so now we're up to what, 2020. So I wrote the paper that led to this work in 2014. So it's a bit old, yeah, like 6 years ago, but it still has really nice. I mean, there's still research questions that we want to answer that, you know, hopefully maybe some of you will pick it up. Okay, so let's see how much time do I have. Oh, I'm doing okay on time, right? How much time do I have overall?
We usually call it at around 6 p.m., but if we go over, it's fine.
Oh, no, I won't go over. I talk very fast, so
Okay.
I don't have a lot of slides, so it's fine. Okay. Okay, so let me, just for now, let's think about that question around random polytopes, okay? So you just think about it as the back of your mind. Somebody proves something hard. Throw points down in a square, right? What's the expected number of vertices? What's the variance for this number? And you want to show it's normal. Okay, so for now, let's just forget about that. Let's look at a different, equally beautiful area of mathematics, random partitions. Okay, so a partition of n is a set of positive numbers that sum to n. Okay, so n is a positive integer. So here's an example. 4, well, 4 can be partitioned as just 4. It's just one partition of size 4. Or it can have two partitions. One is of size 3 and one is of size 1. And we would write 4 is 3 plus 1. Or it can be 2 plus 2. Or it can be, now you can partition into 3 parts, right? One part of size 1, another part size 1, another part size 2. So that's 1 plus 1 plus 2. Or you can do 1 plus 1 plus 1 plus 1. Okay. So the partition is not ordered. So I regard, for example, 3 plus 1 is the same as 1 plus 3. Okay. It's very common in, say, combinatorics to to keep track of these partitions using what's called Young diagram, right? So Young diagram is basically things that looks like Tetris, looks a bit like this, right? Where it keeps tracks of, so yes, you can see here, right? The total number of boxes is my integer n, and then the number of rows is the number of parts that I'm doing my partition into, and then the number of boxes in each row is the size of that part. And Young diagram has this kind of convention that you put the most heavy part first, right? So it's a certain ordering. So you always write 3 plus 1 instead of 1 plus 3. And you represent it by this diagram where the thing on top has 3 boxes and then the thing at the bottom has 1, right? So here, instead of writing, let's say 1 plus 1 plus 2, right? I'm going to write 2, 1, 1, and that corresponds to this picture here. Right. So Young diagram is something you would find a lot if you take enumerative combinatorics. You can prove theorems just by writing partitions and look at Young diagram and do operations on them. It's really fun. In fact, it's so much fun that I think there's an algorithm in combinatorics, and somebody knows French here, so I would embarrass myself because I don't know how to say it in French. But I believe it's said something like something that in English is translated to game of children or something. But it's in French and it sounds much better when somebody knows French say it. So it's a certain algorithm in enumerative combinatorics that prove things about partitions of integers, right? It's very beautiful algorithm. But I last used it when I was a grad student, so I can't tell you a whole lot more about it. I can definitely tell you where to look it up. It's very nice. Yeah, so there are lots of research. I should say this Young diagram also turned up in representation theory of symmetric groups. So yeah, so that has really nice. So it's a good bridge between combinatorics and more analysis kind of stuff. Okay. Okay, so those are some possible applications, right? So now I have a partition and I'm a probabilist by training, so I'm going to make a random partition. How do I make a random partition? That's a question for you guys.
Choose a random n and just write out all of the possible partitions.
Okay, so that would give me a list, like here n is 4. You give me a list of here are the 5 possible partitions. How do I make a random one? How do I choose a random one from here? Should I pick one uniformly at random? Sure, right? So that's one option, right? Now, Elisa, I would tell you that's fair, but that's a lot of work, right? If n is 50, then I just ask you, just return me a random one. And what you're doing is you're enumerating them all, which is computationally very intensive, and then you're going to pick one, right? Is there a better way to construct a random partition that doesn't require so much computation? Somebody else? So I like Elisa's method. It's a bulletproof way of getting one. It just take a long time. Yeah.
Choose k randomly or uniformly randomly between 1 and n. And
Okay.
then you choose like some other j uniformly randomly between 1 and n minus k, and then you choose L between 1 and n minus j minus k, and you keep doing that iteratively until you're until you have a partition of n, basically.
Great. So Ryan's method is what probabilists call like a stick breaking process, right? So here's an example, right? I don't know if you like this Toblerone. I use it because my advisor is Swiss. Or no, actually for a long time I thought he's Swiss, and then somebody told me he's German, and now I'm super like I was very confused because he always told me, because I'm Swiss, I'm going to take a picture, explain this process using the Toblerones. Turns out that was a lie. Okay. Anyway, so what do you do, right? You take this. So this is a famous Swiss chocolate. It's always come in this triangle shape, and it's sort of pre-divided it for you. So just imagine, you have n pieces of this triangles, right? So now you want to create a random partition, well, just randomly break it, right? So break it as Ryan said. So break it, now you have an x1. So you eat it, and now you got n minus x1 pieces left. And now, do it again. So break it, eat another x2 pieces. And now you have n minus x1 minus x2. And then you repeat until you ate everything. And what you have done is to create a random partition of n. Okay. That's great, right? So now again, we want to ask questions about this random partitions, right? You can ask how many, what's k, right? So how many components do you get? What's the distribution of the component size? What happened if I order by appearance versus order by size? Order by size means I list out the pieces like from the biggest to the smallest, right? Order by appearance means I list out like what's the first piece that I ate, what's the second piece that I ate, and so on, right? So being the first piece, you're more likely to be big, but it doesn't mean that you have to be the biggest, right? Because if you choose a number uniformly between 1 and n, you have a positive probability of choosing 1, right? So then you might break off a little small piece, and then the mixed piece might be big, and so on, right? So there's a lot of questions concerning order by appearance versus order by size. This was studied really heavily in, believe it or not, ecology back in the 70s, right? So what happened is there's a very interesting sampling problem. I didn't explain it here. There's a very interesting sampling problem where you basically have, what happens in ecology? Say you go into the forest, you want to figure out what are the different types of animals in this forest, right? So you go into the forest and you randomly set up a tent and you wait for a day. You sit around and you record from your tent all the animals that you can find within your field of vision. Okay. Now there's an obvious problem with this, which is you're not going to find rare animals, right? You're going to find like really common things like rats and raccoons and whatnot. But if there's like a really rare animal like a unicorn, then this method has a really low chance of finding it, right? So then basically this sampling method, the chance that an animal is seen is proportional to how common it is, right? So what you're doing here is called sample. You have a size bias in sampling, right? You tend to be biased. Your sample is not a random sample of the diversity of the animals in the forest. What you're doing is a size bias sample, which is that the more common animals has a higher chance of being in your sample, right? So ecologists was really interested in this and try to correct for it. And also people who do pollings, if you look at presidential polls and stuff like that, there's a lot of discussions about how you correct for getting a more representative sample of the population. Okay. Okay, so those are some aside. Yeah, mathematics is inherently very beautiful, and there's applications beyond this talk. There's connections to things beyond the talk, and I just want to give you some. It's nice to tell stories too. Okay, so let me just look at the question of distribution of the number of components. Okay. Let's just try to figure it out. So here are some simple assumptions, which are x1, the first piece, right, is going to be a uniform number between 1 and n. And then condition on x1, x2 is going to be a uniform number between 1 and n minus x1. And then condition on x1 plus x2, x3 is going to be a uniform between. So basically, I'm just doing a uniform stick breaking, right? So with this, can I figure out what's the expected number of components, right? What's the variance and what's the distribution? Okay. So this is probably the more heavier slides. Let's try to figure it out. So on average, if you pick a number between, 1 and n, so the expectation of that number is n over 2, right? So that's just telling you on average, it's about that you break the piece in half. You don't exactly break it in half, right? There's some fluctuations, but it's about half, right? So if on average, I break the piece into half, right? I have n things, and I would stop until like the crumb is smaller than 1, right? So that means I should really just finish eating it, right? So then how many components do I get? Well, it should be about log base 2 of n, right? So for large n, right, then you can get, with n is really large, then you think about your Toblerone as, instead of thinking about it as a really long Toblerone, you think about it as a discretization of the interval 0, 1, right? You discretize it, that is, you compress your Toblerone so that it looks like is an interval between 0, 1, with the intervals being of order 1 over n. Okay, and now as you send n to infinity, then the intervals just get closer and closer. Okay, so then for large n, right, then what would that be like? Well, then x1 would, now I call it v1. V1 is going to be a point uniformly at random between 0 and 1. And then once I broke off this piece, then now I have a new stick of size 1 minus v1. And now I'm going to pick a point uniformly at random on the stick. And so the piece, the stick that I got left is 1 minus v, and I broke off the piece of size v2. So this size, right, is actually v2 times the size of the smaller stick, which is v2 times 1 minus v1. So then what I got left is 1 minus v2 times 1 minus v1, right? And so on. I recurse this, right? So again, let me just say that. So VIID uniform on 0, 1. So what the portion that remains after 1 byte is 1 minus v1. The portion that remains after 2 bytes is going to be 1 minus v1 times 1 minus v2, right? v2 is relatively how much I take out. So it's the relative size of the byte, of the second byte, right? Because the second byte is v2 times 1 minus v1, right? So what I got left after 2 bytes is 1 minus v1 times 1 minus v2. Now what happens after k bytes? Well, I should recurse this. I should have 1 minus v1 times 1 minus v2 all the way up until 1 minus vk. Okay, so this is a product of IID, right? Vi is a uniform between 0 and 1. So Vi bar is 1 minus that. So that is still, that's still uniform between 0 and 1. And so this is a product of independent, identically distributed random variables. Each one has distribution uniform. Okay, so I'm going to stop when pk, the amount of things that remain, is less than 1 over n, right? Because my Toblerone is like of size 1 over n. So if I draw something that's less than 1 over n, if all I got left is less than 1 over n, then that means my discrete process has terminated, right? So I will stop then. And Tn is the number of bytes taken. Okay. Is there any questions on this process? Is it clear? So I'm claiming the for large n. So this process is a continuous version of the Toblerones, right? The Toblerones is a discrete version in the sense that I pick, if n is 100, then I need to pick numbers, 1, 2, 3, 4, 5 up to 100. Here, by going with the continuous, then I'm allowed to pick any real number between 0 and 100, right? So that's a continuous approximation of the discrete, right? And it's easier to work with the continuous approximation, right? So that's it. So of course, this approximation gets better when n gets to infinity. So for large n, I can say approximately, I cannot immediately send n to infinity because it's 1 over n is going to 0. So instead, I just say, I need some work to quantify this, right? but it's intuitively it's easy to see that the number of the number of parts in my random partition, Kn, that is approximately equals to the number of times that I take this continuous bite from this chocolate. Okay. So now I'm in great shape, right? Because if you know about probability, right, products of IIDs are relatively easy to deal with, right? Because if I take log and I take the negative, because these V's are between 0 and 1. So if I take log, I get a negative number. So if I take negative log, I get a positive number, right? So negative log of this pk is going to be a sum of IID. It's a sum of positive IID, right? And Tn is basically how many, so you have a process, right? Starting from 0, you're going to have these jumps. It's positive, so you can only increase, right? Jumps. And I will stop this process, right, when I go over minus log of 1 over n, which is log n, right? So I'm going to have this process with independent random jumps, and I'm going to stop the moment, the first time that I hit, that I go over log n, right? So this thing is called the number of renewals. This process of positive jump is called a renewal process. And it's so-called renewal process because, you know, it was used to study like the 60s, you know, people were interested in manufacturing and they want to study like, you know, how long does it take until I have to replace like a machine part? Okay, so they assume machine parts fail at random, right? And so if your machine has like, or the common thing in textbook, they call it light bulbs, right? The thing in papers, they would call it machine parts. And then you have a machine has a bunch of parts, right? And then, you know, how long does it take? Well, you know, it's going to be some exponential time until this component fail, and then exponential time until another component fail, and so on. And basically the question is how many renewals, right? How many new parts I have to pay between a time of 0 and log n, right? Which is I let time run until log n, and me as a company, I want to know, okay, in, you know, this many years, like how many light bulbs do I expect that I need to replace, right? Okay, so that thing is called the number of renewals. Okay, so the key point is that there is a very good theory for this. So this slide is maybe a bit heavy if you don't know any probability. But basically, the upshot of that is that you can exactly compute this. You know a lot about the number of renewals. You know the expected value, you know the variance, and you have a central limit theorem, right? So and what you need to compute it is very minimal. You need to know like what's the expected value of one jump, right? That's mu, and what is the variance of a single jump, right? So that's that, and that's easy to compute. So it turns out, you know, for our particular application here, right, then these guys is uniform on 0, 1. This log of blah is exponential. You can compute what it is. And so the number of days to eat the Toblerone is log n. It's not log base 2 of n. It's log n. Okay. And now you think, well, log base 2 versus log, you know, well, how big of a difference is make? It's huge, right? It's huge. Like log base 2, log n is log with base the natural number e, and that is 2.71 something. Log base 2 is log with the base of 2, right? So, you know, if you ever, well, I don't know, if you ever get a mortgage or like owe money to somebody who has like a compound interest, then you care a lot about the interest rate. And an interest rate of 2% versus an interest rate of 2.71% is like a difference between night and day, right? It's like a difference between, you know, an economy that's doing well and an economy that's doing really badly, right? So that log 2 is big, it's huge, right? So it turns out that just little variations in the uniform actually bring about a significant difference in how fast it takes to eat your Toblerones, right? Okay, so now, okay, doing well. Wait, hang on. It's 41, right? Good. Sorry, it's just my clock didn't update. So now I'm into the third act of the part, right? Which is I want to connect random polytopes and random partitions. So just now I plugged in the uniform case and I get an answer. It turns out if you plug in a different distribution for how you eat, right? Instead of picking a point uniformly at random on the Toblerone and blick it, right, I'm going to pick a point according to the beta to 1 distribution. Okay, some distribution between 0 and 1. Okay, plug it in, and then, you know, voila, I get, what do I get? I get expected number of you know, expected of Tn, expected number of bricks is 2/3 log n, and the variance is 10/27, right? And this is, you know, well, you know, before I had this random polytopes, and I get expected number of vertices of my random polytope is 2/3 times r times log n. This guy is, you know, 10/27 times r log n. So that's like, you know, too good to be just a pure coincidence, right? So there must be some way to actually directly use random partitions to prove things about random polytopes, right? So that's what we did in our paper. And by the way, that's not how the paper was conceived. It was not like we noticed there's a 10, 23, and whatever. That was not it. It's just nicer to tell the story this way. This connection we realized after, right? So after we have had a new way to prove the distribution, we thought, oh, you know what? It's actually fairly simple, right? So, okay. So how do I prove, like, what's the connection between random partitions, Toblerones, and polytopes, right? Okay, so okay, so I need to deal with random polytopes. I throw n points uniformly at random in the square. I take the convex hull. Okay. So here are a few things that would help us. Number one is I claim that it is sufficient to study one corner. Okay, what do I mean by a corner? Well, while the outside box is a square, and I'm going to look at points that are, I'm going to like use that square. I look from the viewpoint of one corner of the square. I look at the polytope and I think, how many vertices do I see? Okay, so that's the same as if I drew like a vertical line here, like a vertical y-axis line, and I look at the first vertex of the polytope that I hit. And then similarly, I drew like a horizontal line, and I look at the first vertex of the polytope that I hit. Right. So from the corner, I can only discover vertices of my polytope that lie from here to here. Right. That lie between like the most vertical and the most horizontal guy from that corner. Right. But then, you know, I can repeat this trick for all corners, right? From this corner, I'm going to discover everything from here to here. And then from this corner, I'm going to see everything from here to here. And from this corner, I'm going to see everything from here to here, right? So that and by symmetry, right? I have 4 corners. So by symmetry, if I could figure out what's the expected number of vertices and the variance for one corner, then it's easy to scale it up for all the other corners, right? The other corners are just sums of independent versions of this guy, right? So that's why then you get this expected value 2/3 log n times r, where r is the number of corners of your polytopes of your bounding box. Okay, so that's it. Sufficient to study one corner. It's also sufficient to keep track of the slope. So what do I mean by that? Is to do this, a process like this. So the slope process is, I just imagine I have a stick, right? And I'm going to make the stick. I started out being vertical, okay, and I'm going to use the stick to discover vertices of my polytope. Okay, so I start out being vertical, and I'm going to find this vertex. Okay, and now I tilt the sticks. So I tilted to make it more horizontal. Okay, so as I tilted, I still discover this red guy, but at some instant, the first time that the stick is parallel to this black line here, I'm going to discover 2 points, right? This guy and that guy. And now if I tilt further, then I'm going to my stick is going to be anchored around this point, right? And now I keep anchoring it around this point, keep tilting until I discover this one, and then so on and so forth, right? And so the slope of, so this create a process where as I change the slope of my stick, I either stay the same or I may discover like a new vertex. And as the slope goes from all the way vertical to all the way horizontal, I'm going to discover all the vertices of the polytope that I see around this corner. Okay, so this slope process turns out is the stick breaking process. Okay, that's not a good picture of this. Yeah, so I think it's just too much to explain, like so much math at at 5:45 p.m. So but let me let me explain exactly what the calculation is. Just this is the key to the proof, right? Which is it's like a piece of calculus. It's really nice. It goes, okay, say that my slope is currently like this, right? I'm going to move the slope forward just a little bit, right? And in doing so, I'm going to create this new slope, right? Okay. So now, what's the chance that I discover a new vertex, right? There's only, so the width of this, how much I move forward is like dy, right? It's like a little bit, just a little bit forward. So now, how can I discover a new vertex? Well, the only way I can discover a new vertex is that in this triangle, there is a point of my random, endpoints thrown down on the square. Okay. So if I start from this slope, I tilt it a little bit forward, I sweep out this triangle. If there is no point there, then that means I have not seen a new point to jump. So therefore, I have not created a new vertex. Right? I have not discovered a new vertex. On the other hand, if there is at least one point here, right? If there's at least one point here, then I know for sure that in going from this slope to the new slope, then the new slope would not be hitting my old point anymore, but it's going to hit something here, right? So so condition on the height of the previous vertex, right? Condition on the slopes picking up a new point, right? Then now, if I do discover a point, where would that point be? Well, that point would be uniformly distributed in the triangle, right? Because my points were uniformly distributed to start with, right? And so therefore, because that point is uniformly distributed, I can figure out exactly what's the height of the new point has to be. So if the probability that the height of the new point is y is going to be y0 minus y divided by y0. So you can just take my word for it, but this property, this probability is independent of the slope, right? And not only that, it is proportional to y, right? This, in other words, the height of this process is exactly a beta 2,1, right? This is exactly my stick breaking process. My stick breaking process is literally take the height of the vertices, right, and project it onto the y-axis. Then you get, this value and this value and this value. And I'm saying that this height process is exactly a stick breaking process, right? It's as if you were to take the interval 0, 1 and randomly break it into two parts according to the beta distribution, and then condition on that, you randomly break it into two parts according to the beta distribution again and again and again and again, right? So just by keeping track of this height, then we make a connection with the stick breaking process, right? And when do we stop? Well, we're going to stop when we're gonna stop when basically roughly, you hit the bottom, which is the height, the y height of the point with the lowest y height possible, and that thing turned out to be of order 1/n, right? So that's the same as the previous process, where I'm gonna stop the moment I hit log n, right? And that's it. That finishes the proof, because then by the renewal theory, I have 2/3 times log n as the expectation and 10/27 as the variance, right? So that's the proof. Actually, it took like 10 pages to, like, this squiggle here take like 10 pages to make it rigorous. All these calculations obviously take up room, and so does this. I had a thingy here with a squiggle here. So anything that squiggles in math, right? It means that intuitively it makes sense, but to actually prove it concretely, without, airtight, it can be a fair bit of work. Okay. There's like a difference between getting full credit versus, nagging your professor that you should really pass this class. If you have a squiggle in every single question in the exam, well, probably will be a C, right? Okay, so yeah, so we finished that. So if you like this, I should say random partitions have a lot of applications in computer science, machine learning, so on. I've mentioned a bit about representation theory, about stochastic geometry, high dimensional. Big data is, data points in high dimension. There are works here at UT applying this stuff to wireless communications. So electrical engineering, a lot of folks work on that. Cell biology, Yeah, there are lots of applications. So I hope your just should inspire you to do more classes. Yep. Okay. All right. Well, I think that's it for my talk. I'm definitely happy to chat, have questions or anything. But that's it. Any questions for the talk? I'm happy to take. Yeah. Oh, sorry. I have some chats. Yeah, I don't see these questions in chats. Indestructible phone. Yes, indeed. Yeah, good one. Yeah, it's I used that in Nokia. All of this reminiscent with sweep line algorithm for Voronoi diagrams, but on cracks. What's the sweep line algorithm? Veronica, could you explain it?
So it's also called Fortune's algorithm to construct Voronoi diagrams. I forgot a lot about it, but I had studied it a while ago in high school. But it's the most efficient way to make Voronoi diagrams.
Okay.
I have some
cool.
paper, but I don't remember exactly how. But it's pretty interesting.
It was interesting. Okay, good. I'm glad you found. I'll look that up. That's my first time hearing about the algorithm. Yeah.
Can I ask about one of the things you talked about? I came in a little bit late, so I just wanted to make sure I had it right. So what was the statement? It was the expected value of the number of vertices on our like randomly created convex hole. Yeah, that.
Yeah.
Yeah. So the expected value is like the number of vertices that are like actually a part of the convex hole, right?
So whenever you throw down, randomly many points, then you get one polygon and you get one number that is your number of convex balls, right? So in this simulation, I get 9. But if I were to do the simulation again, I might get 11. And if I do simulation again, I might get 8 and so on, right? So that number of vertices is a random variable, and that has it has an expectation, which is what you would think of as if I were to do this like a million times and take the average, well, what would that be?
Yeah. And so I guess like, because R is the number of size of
R is
size
the number
this,
of
like,
sides.
bounding box.
That's right.
So if R gets like really large and I were to do this problem in like a circle, what does that make the expected value?
Oh, yeah.
Does that like, am I allowed to do a limit on R?
You can do a limit on R, right? But then what is that going to tell you, right? That's going to tell you that if you want to do this in a circle, then the number of vertices should be faster than log n. It grows faster than log n. That's all it's going to tell you. Yeah. But
Okay.
you cannot possibly use this to get a limit like that, right? Because
Yeah.
R goes to infinity, then expected value of Vn is infinity, but that's obviously not true because you only have finitely many points, so you can only have at most n points.
Yeah, that's what I was going to say. So you'd have to do something separate if you want to do the same problem on like
Exactly.
a
If you want to do the
smooth
circle,
polygon.
Exactly, a smooth polygon is like it's a different story.
Is that solved already, or is that an open problem?
Oh, that's a good question. My guess is that the circle should be solved, but like some others general smooth, convex body, I'm not sure. Yeah. So I would say like the higher dimension version of this, there's still some open questions relating to this. I think it was only so very recently, like what happened if you have, I don't know, like a higher dimension convex body, like a more funny bounding box. Like people could only solve the cases where like the distribution of a point is like spherically symmetric or something like that. So there's some open problems that are still around. Yeah.
Okay, interesting. Thank you.
Yeah, no problem. Good question.
So unless anybody has one last question, we're coming up on our time.